Hugo. I'm a PhD student in Ireland, and today I'm going to tell you why you should consider abandoning shading languages. Okay, first, what the heck are shading languages? They're domain-specific languages whose domain is writing graphics programs. The scope can be stuff like materials, light calculations, and image filters. In the offline world, you have languages like the open shading language or the material definition language. And in the online world, or what we call real-time, you have languages like GLSL, which doesn't have a logo, HLSL, which has a logo now, and Slang, which has a very professional logo. So what's the purpose of shaders for real-time rendering? Well, conventionally, we have this pipeline for real-time graphics, and shaders were introduced to replace the stages that I outlined in yellow, whereas before this was just fixed function. We have vertex shaders for essentially performing coordinate transformation, and we have fragment shaders to decide the color of pixels covered by triangles. Since then, we've invented many more shader stages, and Vulkan can have a very complicated looking pipeline. So what characterizes shading languages? The most important thing is that they embrace single instruction, multiple thread parallelism. So you write your program, it's a one invocation, and then you just spawn more of them, quite a few more of them. So your shader is effectively a pure function, and it gets executed in a massively parallel fashion. Shaders, especially the two stages mentioned, they perform so-called streaming computation. So the pipeline provides them with data in some global variable that gets annotated, and the data gets parsed out. And that means that historically, these languages did without pointers. And finally, these languages have historically had a narrow scope because the first programmable hardware was not that programmable. And even if you could program it to do fancy things, the performance budget just wasn't there, so you had to keep your shaders small. So we found out that GPUs are really good at parallel processing, and that can be used for things that are not graphics. And because of that, we have invented languages that are made for general-purpose computation on a GPU. These languages are different because they're open-ended. They're not really domain-specific anymore. They don't have pipelines, inputs and outputs. Because you define your own data layout, you have to have full pointers and define your own buffers and do everything yourself. These languages also tend to support larger programs, maybe even production renderers. And they have things like real function calls, the ability to define complex data structures, the ability to have some sort of template and many higher level features. And they also tend to support unified CPU and GPU programming. So that's essentially sharing a code base between the GPU and the CPU aspects of your code, and sometimes full-blown heterogeneous programming. And that's done, with a single language, at least if you're talking about CUDA or SYCL. The unfortunate thing is there's no real true unified GPU programming API. So in this yellow circle, I have a few examples of APIs that operate with graphics pipelines. You have Metal, DirectX, Vulkan, and so these APIs, they get access to the hardware-accelerated pipeline. They can do texture sampling. They have access to all the knobs. But then you have the red circle here, and that's languages that have access to C++ or some other rich language. And these languages, they have access to full-blown pointers. They can do function calls. They can do recursion. And you find things like CUDA, modern versions of OpenCL, and as well as SYCL. And then finally, there's a third circle. That's the cross-platform, and specifically like being an open standard. And in there, you find all the Kronos APIs, which also includes earlier versions of OpenCL. And these, I wouldn't really say they have full-blown access to C++ languages. They're kind of more like shading languages and how limited they are. So obviously, we'd like to be in the center of these three circles, but there's nothing there, right? That's enough. Okay, so we want to see better GPU languages. We want to have graphics and compute within the same language. But Vulkan supports compute, yes, but you have to use shading languages. So Vulkan is a good starting point, but there's some work to be done. We would like to share our code between host and device. And our third criteria, and I'm going to have to explain what this is, we want to have an embedded language rather than an external language. So what the heck does that mean? So an external domain-specific language, that's a language you create from scratch. It's its own thing. It's got its own grammar. It's got its own type system and its own compiler. Every shading language I've described earlier, and really most of them, bar a few exceptions, they are external ESLs. They are languages that are fully independent. They might be inspired by C or C++ and share a lot of syntax, but they're essentially their own thing. An embedded domain-specific language is when you take a normal existing language, a general-purpose language, and you use the abstraction facilities of that language, such as your lambdas, your syntactic sugar, for you have your implicit, your operator overloading, all these features to sort of create a subset or a library within that language to express some domain-specific knowledge. Scala is a very popular language for domain-specific languages. We don't really use it in this industry, but it's a pretty good example. I can also mention NEDSL. I mean, I have to mention NEDSL, which is the project we have at Saarland to make domain-specific languages, and we can do fancy things like we have a path tracer that's written in this nice, pure textbook code called Rodent, and then it runs really well. And the question I'm asking here is, can we have graphics shader be an embedded domain-specific language in C++? Okay. So what's an embedded shading language like? Well, really it's just a library. You need things like small vectors and matrix math and a few helper functions, and that's mostly what GLSL has. And then the rest of it is just plumbing, for lack of a better word. We have these texture sampling operations here. These are just annotations on functions. These memory types here for the I/O, annotations. The binding model for Vulkan, like these descriptor set things, believe it or not, it's way more annotations. So we don't really need any new language constructs. We can just reuse existing C++ syntax. And these are not keywords, they're just macros defining this header here. So there's this thing called SPIR-V. I'm not going to complain about SPIR-V. SPIR-V is actually really great because before SPIR-V, you had an API, you had OpenGL, and then you had the OpenGL shading language. And that was the blessed language you had to use, and you provided OpenGL with a giant text string, and that was your shader, and OpenGL took it from there. SPIR-V is much nicer. It's essentially it's called an intermediate representation, which is a file format defined to be consumed by compilers. It's essentially like a sort of pseudo-assembly. And that's very nice because it means Vulkan can theoretically work with any language. The problem is that even though SPIR-V is used by both OpenCL and Vulkan, it doesn't actually have the same features depending on which language you're using. It's not unified. And there's this notion of a kernel dialect for OpenCL, which has access to things like nice pointers, function calls, and whatnot. And then you have the shader dialect, which is what Vulkan is bound to. And well, it's not great for us. Pointer usage is severely limited. We'll see a bit more on that. There's no generic address space, so every pointer has to refer to a specific address space. There's no such thing as just having T star, and that can be wherever. There's no recursion. There's no function pointers. And like, a lot of things are, there's a lot of extensions and quirks, and it's a quirky format, and it's not, if you're starting with a normal compiler representation like LLVM, and you're trying to go to SPIR-V, there's actually a lot of these things in the way. Okay, so what the heck are logical pointers? So in the shader dialect of SPIR-V, you have this notion of addressing mode, and shaders have to use the logical addressing mode. And what that means is if you have a pointer to something, if you have, say, a pointer to something, I have my struct S, I have a pointer to it, I can take my pointer to the struct and turn it into a pointer to an integer within that struct. That's fine, even though that's syntactically incorrect. But if I try to do something like access the next element in array contiguously, that is not okay, because that is not a sub-object of my initial object. And likewise, if I had a pointer to an int and I tried to upcast it to a pointer to an S, that's also not okay because it's not a sub-object. The second rule with logical pointers is that you cannot change the type you're pointing to. So if I have a pointer to int, and I want to reinterpret it as a pointer to a float, that's not okay. And finally, pointers themselves are not first-class values. What that means is there's a lot of things you're just not allowed to do with pointers. For example, you can't pick between two pointers. With pure logical addressing, this is illegal. So if I have a Boolean here, and I want to pick between pointer A or B, not okay. And if I want to have a struct that contains a pointer, so if I want to store pointers in memory, that is also not okay. So you can't load and store pointers. That is extremely limiting. Your pointers are more like C++ references that you can't copy. It's extremely crippling. So some solutions. The first thing is something called pointer canonization. So in our compiler, we sort of look at pointer expression and we try and make them all have the same shape. We try and put all the casts at the end and all the indexing at the start. So we try and get rid of any spurious casts we can avoid. We also support demoting. So if you have a pointer and we know it's representable with only these logical operations, we leave it as is. And otherwise, we emulate pointers with arrays. So that looks something like this. We have a big, for example, we have the private, like thread private memory. We're going to say, OK, we want 4 kilobytes of thread private memory. And all our individual allocations are going to be ranges within that array. And to load data and also data into this array, we just use offsets, and we bitcast the individual values. So on load, we bitcast the value, and on source, we also bitcast it. So the array only deals with integers, but we can have whatever we want, and we can perform our casts, and stuff works. This looks and sounds really crude, and we benchmarked it, and it actually performs better than you'd think. Similarly, we have issues with function calls. As I said, they cannot be recursive. They don't. Functions don't have addresses, so a function is also not a first-class value that you can like store to memory or whatever. And in fact, you cannot call anything indirectly. You can only call functions if you say exactly which function you're calling. There's no such thing as function pointers. So the solution is less easy to explain. We do this thing called continuation passing style transformation, which will speak to some compiler nerds in the audience, but maybe not everyone. And what that leaves us with is code that only does tail calls. So there's never a normal call where we go to the stack and pop after that. We just always go to the next thing directly. It's just like only indirect go-to. And then we have a software scheduler to emulate, because the tail calls are still not allowed in SPIR-V. The software scheduler is something like this. We have a top-level loop, and the top-level loop has a bunch of indices. It receives an index, and this index is what function to run, or rather what continuation. And each of the continuations, because it's not allowed to do a tail call at the end, it just returns another index back to the dispatcher, which will call on to the next thing. And that lets us do pretty much arbitrary function calls and control flow within the bounds of the scheduler dialect of SPIR-V. OK, cool. OK, so what we've built here is a compiler. It's called the Vulkan Client Compiler, VCC. It lets you compile standard C++ to your shaders, and you can use it for any Vulkan shader stage. Theoretically, we haven't tried them all. It's based on an unmodified Clang front end, which is noteworthy because you don't want to be maintaining a fork of Clang somewhere. And we use this thing called the shady intermediate representation, which is essentially it's a SPIR-V-like thing we've made, but it's very tuned to the task of, OK, doing these array transformations, these logical pointers, dealing with them, optimizing them into something nice. As input languages, we support LLVMIR, which is how we make VCC happen. We invoke Clang, we tell it, OK, compile our thing, and then emit LLVMIR. We parse that, and then we turn it into what we need. We also support eating the kernel-style SPIR-V from OpenCL. So if you want to go that way, that's also an option. And as outputs, we support shader SPIR-V, so that's your nice Vulkan-compatible shaders. Also GLSL for fun. CUDA, because it's useful for evaluation, it gives us a reference. And also ISPC, because ISPC is a host language with debug symbols, so we can run our code and see what's going on. But it's still a vectorized, it's still a SIMD language, or a SIMD, right? So we can debug our code and figure out why it doesn't work, instead of just hanging the GPU and being stuck with it. OK, so our headline application for this paper is we made a real-time path tracer with it. It's very conventional. It's a GPU path tracer written entirely in software. We don't use Vulkan acceleration structures. We didn't have the time. It does implement, therefore, a custom BVH. We do next event estimation. We have dielectric materials. It is not the fanciest thing, but it is a significant workload. It was written by someone who isn't a compiler author, my colleague Ömercan, over there in the audience. Hi, Ömercan. Great work. And that's significant as well, because usually these custom small languages, they're made by someone, and that someone writes software with it, and that's the only software that will ever work with it. And this path tracer can compile to both CPU and GPU, and we can even switch on the fly. So it's really a unified code base. We just have a header, and it goes, OK, if compiling with VCC, then use these intrinsics, otherwise include stud math and whatever. And we have the 3 scenes here. We have the kernel box, we have the bedroom scene, and the dining room scene. OK, let's look at some performance results in the same order as before. So for the kernel box scene, and lower is better, we have the CUDA reference. Oh yeah, we have a CUDA reference, by the way. This path tracer also compiles to CUDA, of course. That's how we get a reference. And essentially, depending on the scene, so the kernel box is the worst, and the other room scenes are pretty OK. We are between 0.5 to 1x the performance of CUDA, just straight up CUDA, which I would say it's not bad for a toy compiler made by a couple PhD students. It also happens to just work on AMD, on both the RADV and AMD VLK drivers. So portability, yay. And it mostly works on Intel and Apple through Multi-NVK. Anyone who deals with GPU stacks knows that it's a nightmare because there's bugs in everything, your software, but also their software. It can be made to work. There's no actual blocker. It's just we didn't spend the extra engineering time to make sure the path tracer fully runs on these platforms. It does run if you only run primary arrays. There's something wrong with the recursion. We'll get it. It's fine. We can also apply this to conventional graphics. That's our second application. We have written this really cute application with the fragment shader and a vertex and fragment shader. And it is a procedural terrain demo, which you've seen many times, this kind of thing on Shadertoy and elsewhere. We wrote it in GLSL as our reference, and then we just ported it. And I believe, I'll attempt this, I believe I can run it in real time. So this is the GLSL version. Yeah. Yeah, no, this is programmer art. It doesn't look brilliant. So we're running at what? Well, yeah, 120 FPS. That's different now on the projector. And if I run it with the shaders we compiled with VCC, it looks identical and performs identically. Oh, it's because I'm running on battery. OK. I was getting 200 FPS before on both. You just have to trust me or check the paper. Or run it yourself. I'll get to that. Cool. So that's the demo passed us. So yeah, we pretty much saw identical performance no matter where we tried this thing. And the reason we figure the performance is identical is because we're not actually using any fancy feature that we have to emulate and do anything crazy. We just have a bunch of sine and cosines and Perlin noise stuff. And it's a known number of iterations, so the compiler can just unroll it into a big giant ball of math operations. And it looks the same no matter who generated the ball. The shader compiler just goes through it and makes it into something decent. OK, so in conclusion, C++ for Vulkan, that's a viable thing. I think we have demonstrated that. All the code is available under MIT license on GitHub. You can scan this QR code to our website. The compiler, the applications, the benchmarks. I would propose the idea that shading is just a thing a language does. It's just a workload, a use case for a language. It's not a class of language, or at least it can be seen this way. We're very excited to see what can be done with this technology, both for us as future work, but also for other projects. There's nothing C++ or Clang specific here. We just pass LLVMIR and then run this complicated transformation pipeline on it. You could just use this for your own language. I mean, Slang can use this. GLSL, if GLSL wants to be modern, they can use this. Zig, whatever, Rust, it's all possible. And yeah, I think there's a lot more we can do in the idea of unifying and simplifying GPU stacks by sort of moving on to more general purpose languages. OK, and I think I can take questions now.
Okay, I don't even need to start asking for questions. First hands are coming up directly.
Thanks. Great work. So if I understand everything correctly, you still have to write the host code in conventional, with the conventional Vulkan API?
Yes, we only tackle the shader part of the equation. We don't tackle the entire thing. But still due to write a PhD thesis, so maybe we'll get there. But so this is strictly a compiler for your shaders. I don't offer a solution to the 1,000-line Vulkan example. This is not what this is about. We're just dealing with the shader question.
So my question is, if I'm writing the host code in C++ and the shading code in C++, why have two different compilation processes? Or do you think you can overcome that and have a unified model?
I mean, okay, so you have to invoke the compiler twice, right? We don't do the CUDA thing where you can have both code in one thing and it generates the. That is more. There's nothing. It can absolutely be done. It's more compiler engineering work. It has less scientific obvious value for us to do all this nice ecosystem thing where you have a nicely packaged thing. Currently, what we do is we just have a bunch of CMake scripts that deal with this for us, and I mean, you can absolutely, theoretically, this should be I think this should be a feature of, normal Clang. Clang should just come with a flag to do this. It just doesn't, but hopefully in the future, things like that start appearing.
Okay, thank you.
There, I already see the next question.
Great presentation. I agree, your point about metal and the bound pointers and argument buffers, they're not real pointers. Vulkan, I realize how hard it is to keep up to date with the APIs. Vulkan has buffered device addressing, and I was just wondering have you looked at it, and what are the limitations that you see with BDA?
We do use that for global memory. We also support non-physical global pointers, so if you want to use shader storage buffers the old-fashioned way, you can also do that. So we don't actually come with. The compiler tries to not be opinionated about how resource binding happens. I mean, my opinion is that you should make everything bindless and don't even think about bindful, but that's just my opinion, and the compiler doesn't.
Yeah, totally. My comment was because you said that Vulkan didn't have pointers, but...
Right. Well, it does have those, but only for global memory. Everything else, you're stuck with logical pointers.
So, anybody else?
Hi. So way back when we had a MIMD GPU, but it soon was killed off for SIMD/SIMT. But obviously, what you're suggesting with all these sort of like function pointers and stuff, how often do you get into divergence hell, basically?
Not any more often, but with a switch case.
Okay, fair enough. But what I want to know is, if a user sees this, are they going to be expecting it to go as fast as it would on the CPU, and then suddenly get a rude shock to find that it isn't?
I think, so you should use this and assume it to be as fast as running this on CUDA before they had independent program counters, or AMD with SYCL and function. So the issue is, if you run a divergent function, you're going to have a scalarization loop where it iterates over every unique value, and it runs that code path and then runs the next one. But because the function pointer itself is a value, you can just do the thread sorting yourself. You can look at I'm trying to call these pointers, and then you have a local voting thing where all the threads agree, we have enough threads trying to run the same function, let's run it. Or if you don't, you put it in a queue somewhere, and then you could run it later. This is fully up to you, the function pointers. Because they're just first-class values, you can manage the issues of divergence and thread sorting and compaction yourself. You're given this power.
Okay, unfortunately, we are out of time and already in the coffee. There's one more question. I think in the coffee break, you should probably sync with the person who still has the question. Let's thank the speaker again.